Let's start with something that looks simple. You have users. They send requests. Those requests go through an API gateway and end up in a large language model. 10 million requests per day. At 2 cents per request, that's $200,000 a day. Just inference. No training, no fine-tuning. And most teams look at this and think, okay, we understand the cost. But this diagram is lying to you. Most teams think this system is simple. A user sends a request. The request goes through an API gateway. The model responds, and you pay per request. That mental model feels clean, predictable, comforting, but it's also dangerously incomplete. Because real systems don't process requests. They process traffic patterns, bursts, retries, background jobs, edge cases. What looks like a single request on a diagram is rarely a single request in production. A single user action often fans out into multiple calls, authentication, context retrieval, vector search, reranking, safety checks. Each step is small, each step looks cheap, but the system doesn't see one request, it sees multiplication. And that multiplication is invisible if you only look at the diagram. This is where most cost models fail, not because the prices are hidden, but because the system behavior is misunderstood. You don't get billed for what you intend to run. You get billed for what the system actually executes. And at scale, those two are never the same. At small scale, none of this feels dangerous. A few cents per call, a few extra milliseconds of latency, nothing that triggers alarms, nothing that forces a conversation. But scale changes the rules, not slowly, not predictably, abruptly. Because traffic is not linear, it's layered. One user becomes 100, 100 becomes 10,000, and every hidden operation is multiplied by that growth. That vector search step, it doesn't run once, it runs for every request, sometimes more than once. That re-ranking pass, also per request, sometimes per tool call, safety checks, moderation filters, logging, retries after timeouts, fallback paths when the model hesitates. Each of these feels cheap in isolation. Each of them passes code review. Each of them looks reasonable. But systems don't execute features. They execute combinations. And combinations are where cost stops being intuitive. This is the exact moment where proportional thinking breaks. Your user growth might still be linear. Your product metrics might look healthy, but your infrastructure cost is now compounding, quietly. And this is why teams miss it. Nothing is broken. Latency is acceptable. Error rates are low. No alerts are firing. The system is doing exactly what it was designed to do. Until one day. The cloud bill jumps. No deployment. No configuration change. No new model version. Just more traffic flowing through the same architecture. The diagram didn't change. The pricing page didn't change. But the math did. So where does this break? Not in pricing, not in the model, and not in the cloud provider. The failure happens earlier. In the way the system is conceptually modeled. Most teams model LLM costs as if they were API calls. Input goes in, output comes out. Cost equals tokens times price. That model feels reasonable. It worked for traditional services. But it collapses under AI workloads because it assumes isolation. It assumes each request is independent. No memory, no feedback, no internal decisions. But modern AI systems don't behave like stateless services. They behave like agents. They observe, they evaluate, they decide what to do next. And the API gateway is where those decisions live. It doesn't just forward traffic, it reacts to it. Once you introduce decisions, you no longer have a pipeline. You have a control loop, and control loops don't scale linearly. That's the mistake hidden in the diagram. Not that it's wrong, but that it quietly ignores behavior. This is where the real formula appears. Not cost per request, not cost per user, but cost multiplied by n. And n is not traffic. N is behavior. It's how many times the system decides to call the model again. Retries, tool calls, reranking passes, fallback paths. Each one increments n, and none of them are fixed. N changes with user input. It changes with latency. It changes with partial failures. Two identical users can generate completely different costs. Because the system is adaptive, it reacts to uncertainty. It explores alternatives. It tries again when confidence is low. That's what makes modern AI systems powerful, and that's what makes them expensive. Traditional cost models assume n equals 1. One request, one response, one billable event. But in real systems, n is rarely 1. It's often 5, sometimes 10. And under load, it can grow without warning, especially when timeouts overlap, especially when retries cascade. But here's what makes this dangerous. N doesn't just grow with scale, it grows with complexity. Every new tool you add, every guardrail, every fallback, every safety layer, each one introduces new decision paths, new branches, new chances for the system to invoke the model again. And here's the critical insight. You don't control n directly. There is no max n switch. You influence it indirectly through architecture decisions, prompt structure, timeout budgets, retry policies, tool orchestration, guardrails. Each decision feels small. Each one passes review. But together they determine whether n stays bounded or quietly grows until it dominates your bill. This is why cost explosions feel sudden. N was growing the entire time. You just weren't measuring it. This is what happens next. Teams don't notice the cost increase immediately. They notice it indirectly. Margins shrink, forecasts drift, latency budgets tighten. Product decisions get delayed because every experiment now has a price tag. And slowly, the AI system starts to feel expensive, not because it failed, but because it worked exactly as designed. At this stage, inexperienced teams panic. They start cutting prompts, switching models, optimizing token counts without understanding the system. Mature teams do the opposite. They slow down, they zoom out, they stop asking, "How do we make this cheaper?" and start asking different questions. Where does N actually grow? Which decisions trigger retries? Which user paths explode under load? They stop measuring tokens and start measuring behavior. They introduce budgets, caps, back pressure, not to reduce intelligence, but to constrain it. Because intelligence without constraints is not innovation, it's risk, and cost is simply the first signal that risk has escaped control. So this is the model to keep in your head. AI costs don't grow because models suddenly get more expensive. They grow because system behavior becomes harder to predict. Every retry, every tool call, every fallback path, every internal decision adds another layer of uncertainty. And uncertainty is what turns linear pricing into nonlinear cost. The mistake isn't using powerful models. The mistake is deploying them as if they were static services. Because in production, intelligence is not free. It has shape, it has dynamics, and if you don't model those dynamics explicitly, they will show up somewhere else, usually in places you didn't expect, and almost always on your cloud bill. If this feels familiar, it's because this isn't really an AI problem. It's a systems problem. In the next video, we'll break down how real teams actually cap N in production, not with theory, not with best practices, but with concrete architectural choices that keep costs predictable under real load.